everybody. Welcome to the next section in Unit 12, which is all about phase diagrams. So far you've learned about the different types of solids, and you've talked about the types of intermolecular forces that molecular solids can have. And you started to rank those different types of materials in order of increasing or decreasing boiling or melting point, depending on what type of molecule they are and the type of intermolecular forces those particles have. So of course, we've been talking about phase changes so far. And of course, phase changes going from a solid to a liquid to a gas, or whatever you want to think of. Phase diagrams, I think, are relatively easy to understand, but it does take a little bit of time to just kind of get some practice with them. So in class, we're going to see some examples of phase diagrams, and you'll interpret them using a little activity. So knowing all of that, let's talk about what a phase diagram is. So a phase diagram is a graph, and it's a graph of pressure versus temperature. And this graph of pressure versus temperature shows the conditions under which the phases of a substance exists. So generally they'll look a little something like this. Now this is a very generic phase diagram. So on your x-axis, you will have temperature, and temperature can be in any unit. It could be in degrees Celsius, Kelvin. Ultimately, it doesn't matter. And pressure is going to be on the y-axis, and units of pressure could also be in anything. It could be atmospheres, torrs, millimeters mercury, whatever, sometimes kilopascals even. So it's pressure versus temperature, and this will outline the conditions at which you will find the three states of matter for any compound. So generally it looks like this. So notice I have solids on this side, I have liquids in the middle, and then I have gases down here towards the bottom. I tend to remember this by the acronym SLUG. Sounds kind of silly, but that's literally how I remember it. So going all the way across here, I have S, L, G. G's a little bit lower there, but it's always going to be in that order. So solid, liquid, and gas. You'll see a couple of very special parts to this. And the most special part right here is this triple point. And that triple point is where you have all of those states of matter that exist at one point. And we'll look at this after we define each of these terms and look at an actual phase diagram for water. There's also something known as the critical point. And the critical point is also a very crucial part of a phase diagram. It's very critical. Really lame joke, but whatever. Let's go ahead and get some of these definitions down that you need to understand and know. One of the most important points of a phase diagram is the triple point. And the triple point tells us the exact pressure and the exact temperature at which you can have a solid, liquid, and gas or vapor of a substance coexisting. At those conditions, you will have all three phases of matter present in a sample, which is really darn cool. There's a lab that I always wanted to try. It's the phase diagrams of carbon dioxide or dry ice. I don't know where to get dry ice from. I guess I can try to look it up somewhere. But you can have all three phases of matter of carbon dioxide in one sample in our lab at one point in time. I really have to try to work on that. But yeah, specific temperature and pressure where all three phases of matter can coexist. There's also, which is something known as the normal. And notice I put boiling, freezing, melting point. The key word here is normal. And normal tells us the temperature at which a substance undergoes a phase change at 1 atmosphere. And of course, 1 atmosphere is at standard pressure. Standard pressure. So this would be if you were on the beach, right? If you're at 1 atmosphere, what's the normal freezing, boiling, or melting point of that substance? Of course, if the pressure changes, if you are down below the surface of the ocean, or if you are on top of Mount Everest, because the pressure is different, a substance will boil or melt or freeze at different temperatures, which is really cool. The critical point of a substance indicates the critical temperature and pressure. And I hate definitions like that. It's like it has the word in there when like you're trying to find out what the definition of the original word means. So let's break each of those down too. So critical point indicates the critical temperature and pressure. Well, what's the importance of those two values? The critical temperature is the temperature at which the substance cannot exist in the liquid state. So you have a temperature at which this particular substance can no longer exist as a liquid. It can't happen anymore. It has to be a gas, or it's what we call a supercritical fluid, which is one of the other definitions down below. So above the critical temperature, we no longer have a liquid. And the critical pressure is the lowest pressure at which the substance can exist as a liquid. So if you are higher than the critical temperature and or higher than the critical pressure, you can't have a liquid anymore. Okay, it's what we call a supercritical fluid. It does not have distinct liquid and gas phases. It kind of makes its own new state of matter, which is really interesting. I didn't learn about a lot of this stuff till I was in like grad school, so we're not going to talk about that. But just so you know, anywhere beyond the critical point is where we have a supercritical fluid, which means we can't differentiate between a solid and a liquid anymore. So let's go ahead and just look at a phase diagram for water and take a look at some of the different parts of this. Like I mentioned, the most important part is this triple point right here. And this triple point is where all three states of matter coexist. So I have solid, liquid, and a gas or slug. So solid, of course, is the S right there. Liquid is the liquid. And then I usually call this as a gas. So we'll put G for gas there. Slug, it always goes in that order. At these conditions, so it looks like this graph is at a unit or is in units of degrees Celsius for temperature and atmospheres for pressure. So your triple point, if you were to identify what conditions all three states of matter coexist, we would have a temperature of 0.01 degrees Celsius and 0.0060 atmospheres. If we were to have water at those conditions, you would have ice, liquid water, and gas, water vapor, all in the same system. Very difficult for us to get that though at our conditions. I mean, this pressure would be like almost in space, right? Probably even less than the pressure of space. So very, very, very low pressure. We also have something known as the normal freezing point. So again, normal is always at 1 atmosphere. So notice here that this line is the normal and this is at 1 atmosphere of pressure. Oops, right there. And because I'm going from a solid to a liquid, going across this line would be melting. So by increasing the temperature, but keeping the pressure constant, so as I'm going across this 1 atmosphere of pressure line and temperature is increasing, we can get water to melt. If I have a constant pressure, let's say going in the opposite direction, maybe starting from 20 degrees and going down to a negative temperature, we can have this start to freeze. And remember, something for it to be frozen doesn't mean it has to be cold. It just has to be in the solid state of matter. Frozen just means that the particles can't slide past one another. And if I continue across, so this is the normal freezing point or the normal melting point. It depends on what direction you're going. Of course, the freezing point and the melting point are the same. Water freezes at 0 degrees Celsius, but water also melts at 0 degrees Celsius. Still at 1 atmosphere of pressure. So as I go across this section right here, I get to its normal boiling point. So I'm going from a liquid to a gas. And of course, going from a liquid to a gas means you are vaporizing. Vaporizing. I'll say vaporization instead. We don't usually use evaporation. Evaporation is more so just for water. Vaporization is a really better term for any substance. And if I have a constant pressure and I'm lowering the temperature and I'm at a gas, going from a gas to a liquid, we know that process as condensation. So you see condensation, of course, if you take a hot shower in the cold winter months, that water vapor from that steam from the shower hits the cold window and it starts to condense. You might say liquid water on your mirror after you take a warm shower in the winter. We also have another point as well, or another phase change to look at, and it's this little tiny section right here. And for water, it's very difficult to do this, but you can in fact get water to skip the gaseous phase entirely. So going from a solid to a gas, we know this process as sublimation. So let me write it right here. So sublimation or subliming. Any substance can sublime. It goes from a solid to a gas, skips that liquid phase entirely. You can also go from a gas to a solid, and we know this process as deposition. And you see this if you drive and you go, I think I've mentioned this in the Chem 1 review video, but you get out in the morning and you don't park in a garage, that really cold water vapor from overnight hits that cold windshield and you get those ice crystals that are really annoying to take off when you're running late for school. That's a result of deposition. It turns from a gas in the air and it hits the cold windshield and turns to a solid straight away. Anywhere along these lines, you have those two states of matter that coexist. So here, if I'm at these conditions, let's do this in a different color. If I'm at these conditions right on that line, I would have a solid and a gas coexisting in the same container. If I'm right here at these conditions, whatever that might be, I would have a solid and a liquid coexisting together. If I'm right here at those conditions, I would have a liquid and a gas coexisting. We call that equilibrium. And you've heard me mention that word a couple of times so far. We don't talk about equilibrium in Chem 2. That's definitely an AP subject. But equilibrium just means that they both exist together in one system. Up here, this is another very crucial point. This is known as your critical point, like I was mentioning. So let's get a different color. Let's do yellow right here. This is your critical point. And your critical point tells you the critical temperature. So if I go down this line, I have this section here, and it tells me the critical pressure. So the critical pressure is all the way opposite this here. Anywhere beyond those conditions, so if I am above this line right here, I have surpassed the critical pressure. So pressure's too high. If I am anywhere on this side of the system, I've surpassed that critical temperature. Once I'm anywhere in that system, having a hard time with this pad here. Once I am anywhere beyond either one of those points, that's where we have what's known as a supercritical fluid. So I'm just going to keep this all in yellow. Supercritical fluid. And remember, a supercritical fluid means we kind of have this weird new state of matter where we can't distinguish between a liquid or a gas. It's kind of like another new weird state of matter. But these conditions are crazy. I mean, 217.75 atmospheres. Imagine that your weight is 217 times greater than what it is now because the atmosphere is pressing on you that much. That's a crazy pressure. And it's also a crazy temperature. It's, 373 degrees Celsius, which I can't even fathom how high that is. But it's a very, very high temperature. So beyond that point, we can no longer distinguish between a liquid or a gas. That's its own entity, which is a supercritical fluid. So like I was mentioning, the normal freezing point, melting point, boiling point, whatever you're talking about, this is all at 1 atmosphere. So if you're not at 1 atmosphere, the temperature at which you're going to undergo a phase change changes. So you might have heard before that when you go, let's say, to Colorado, I know a lot of students tend to move out west after they graduate, but you might have heard something that water doesn't boil at 100 degrees there. I don't know why you would have heard that. I feel like I might have heard that when I was in high school. I don't know, but anyway, water doesn't boil at 100 degrees. It's actually different than that. And you could figure out what temperature water would boil at. Would it be less than 100 or would it be greater than 100? So let's say that we are, like we said, in Colorado on the highest mountain that there is, doing a chemistry lab. For whatever reason, we don't know. But for the sake of this, let's just pretend. So like I was saying in a video before this, I think it was in the gas selling unit, if you are standing on a beach, right? So here's the ocean. And if you're standing on the top of the mountain, obviously you're not going to stand on the ocean unless you're on a boat, and then you're standing on the top of the mountain. So here you're in Colorado. Here you're in California on the beach. So you have a lot more atmosphere that's on top of your head if you're at sea level. So sea level, you're at a pressure of 1 atmosphere. Whereas if you're standing on the top of a mountain, there's not as much atmosphere that's on top of your head. So you're at a much lower pressure. I'm just going to put lower P, lower pressure, if you're on top of a mountain. So what happens to the boiling point of water if the pressure is much lower? Well, let's look. Here's water's normal boiling point. And if the pressure goes down, which is what I'm noting here, the boiling point actually also goes down. Let's look. So here, when the pressure is lower, the boiling point gets below 100 degrees. Maybe this is at about, 90. I'm just estimating here. So the boiling point of water actually goes down when pressure decreases, and that's because that water is able to evaporate because it's not pressing down on that surface as readily. Let's say you're below the surface of the earth. So here's the ocean again, and you're in a submarine. Down below there, there's a little submarine. You not only have the air that's on top of your head, but you also have that really heavy water that's on top of you. So pressure is really, really high. We're at a very high pressure down below the surface. Of course, if you're in a pressurized cabin, then that's different. Hopefully you're in a pressurized cabin. But if you're at a higher pressure, what's going to happen to the normal boiling point? If you're at a higher pressure below sea level, so here we're going up, higher pressure, the boiling point for water actually increases. Maybe it's 110 degrees Celsius. So depending on the pressure, the boiling point can change. And that's why we have a specific definition for the normal boiling point. We know that water boils at 100 degrees, but if we boil water in our lab, it's probably not going to be at 100 degrees because we are not at atmospheric conditions. We are not at sea level in Hawley, Pennsylvania. This is a lot of stuff on this, but I think that just getting some practice with phase diagrams is really the way to learn more about how to use them. So you're going to manipulate, I think there's 6 phase diagrams in an activity around the room, so you can get some practice with using these phase diagrams. As always, if you have any questions, let me know. Stop by and see me. Make a note in your notes so you remember to ask me that question. Otherwise, I will see you in the next video. Bye.